الشبكة العالمية للعلماء الجزائريين إيناس هي منظمة غير ربحية تأسست عام 2016 من قبل أكاديميين ومهنيين جزائريين مقيمين في الولايات المتحدة الأمريكية. الهدف من وراء تأسيسها هو رد الجميل للوطن والمساعدة في رفع مستوى التعليم في الجزائر. مهمة إيناس هي ربط الكفاءات الجزائرية في جميع أنحاء العالم مع نظرائهم في الجزائر. من بين أنشطتها نظمت إيناس مؤتمراً مهماً عقد خارج العاصمة واشنطن في الولايات المتحدة الأمريكية عام 2019. حدد المشاركون في المؤتمر عدة قطاعات حيوية تحتاجها الجزائر، واتفقوا على العمل في 10 مشاريع تغطي مجالات مختلفة نذكر منها التعليم والرعاية الصحية والزراعة والسياحة البيئية إلى آخره. والعمل في هذه المشاريع لا زال قائما. تستخدم إيناس أكثر المناهج العلمية تطورا من أجل تسيير ومعالجة هذه المشاريع. البداية المتواضعة لإيناس تضمنت عددا قليلا من الأعضاء، وهي اليوم تضم مئات الجزائريين الأكفاء من جميع أنحاء العالم. هدفهم هو المشاركة في رد الجميل والمساهمة في بناء جزائرنا الجديدة. هذه الثلة من الكفاءات الجزائرية الفخورة بوطنها تجمع بين التنوع والخبرة مع الاستعداد والرغبة في تمهيد الطريق من أجل مستقبل مشرق للجزائر. تستخدم إيناس منصة تقنية جد متطورة تسمح للأعضاء بالتعاون وتبادل الأفكار والخبرات. كمنظمة قائمة، إيناس لديها أقسام عملية مختلفة تضمن الدعم المحترف لجميع أعضائها ومشاريعها وتظاهراتها العلمية. نرحب بكل الكفاءات الجزائرية في العالم للانضمام إلينا في هذه المهمة النبيلة. الجزائر أكبر منا جميعا، فلننهض ولنترك بصمتنا.
السلام عليكم ورحمة الله تعالى وبركاته. مرحبا بكم في هذا اللايف الجديد من الشبكة العالمية للعلماء الجزائريين إيناس. إذا اليوم هذا الويبينار هو لا سويت تاع لا سيري تاع الويبينار في جيو ساينسز مع الأستاذ عبد الكريم أوديا والأستاذ محمد عمروش. إذا قبل ما نبداو برك بغينا نفكروا الناس اللي راهم يتبعوا فينا بداية تاع حملة التطوع تاع الأكسجين. أنا إيناس قدينا نليموا 73,000 دولار في هذه الحملة، واللي غادي تكفينا باش نوزعوا 50 مكتف أكسجين للجزائر بإذن الله. إذا غادي نشرع في هذه الأيام، سوف نشرع في عملية الشراء ونقل هذه المكتفات الأكسجين ونوزعها إن شاء الله على عدة ولايات، على عدة لي زوبيتو تاع ونالجيري. هذا فقط بين قوسين. إذا مرحبا بكم أستاذ عمروش ومرحبا بكم عبد الكريم أوديا. نخلي لا بارول لك.
Merci, يعطيك الصحة، بارك الله فيك. J'espère que vous allez tous bien dans ces moments un peu difficiles que vit l'Algérie en ce moment. إن شاء الله تكونوا قاعد بخير. دونك معكم محمد عمروش من اليابان دائما. I am the group leader of the geoscience group with INAS and I am also leading this project earthquake hazard mitigation. إن شاء الله we are trying to promote earth sciences and earthquake sciences to the general public by organizing monthly webinars. نعرضوا chaque mois un spécialiste dans le domaine parasismique ou la sismique dans du domaine géologique, géophysique, ainsi que dans le domaine structural. Parce que comme je le dis toujours, c'est pas les séismes qui tuent, mais ce sont les constructions. Donc, لازم علينا نتعلموا مليح ce qui se fait dans ce domaine afin de toucher un maximum de pays. Donc, اليوم إن شاء الله in this sixth webinar, we have Professor Abdelkrim Aoudia, who honored us to present this lecture. السلام عليكم عبد الكريم، مرحبا بك معنا.
Bonsoir.
Bonsoir, merci d'avoir accepté notre invitation. Donc, je vais essayer de brièvement faire une petite introduction de notre panéliste aujourd'hui. Donc, Professeur Abdelkrim Aoudia took his degree in geotechnical engineering from the University of Algiers in 1991 and then worked with the CRAG from 1992 to 1993. In 1994, he moved to Italy, where he got a PhD in seismology in 1997 and then went through different postdoctoral research positions up to 2003 when he got habilitation of professorship in Italian university system. In 2004, Professor Aoudia was the project manager of the first large European and transnational initiative in GPS geodesy that has led to the setup of the network of more than 160 stations across the European Alps. In 2005, he also was selected for a senior scientist position at the National Institute of Oceanography, Experimental Geophysics, and the same year won an international vacancy call as the coordinator of the Solid Earth Geophysics Group with ICTP, International Center of Theoretical Physics in Italy, who is also working on for the moment. Karim's jobs includes both scientific research and capacity building in developing countries. I hope I didn't miss the part of it, Abdelkrim.
Yes, we.
Thank you very much. So with that said, without further ado, I will leave you the floor and we can start the webinar today. Please, Doctor.
Okay, merci Mohamed, merci, c'est très gentil, and let me switch to English. I will be speaking English, but my English is extremely simple and would be very understandable to anyone. So I don't feel quite comfortable to speak in French, to tell the truth, but I will be ready to answer questions in French, in Berber, in Arabic. So no problem. So let's get started. So what I will do, talking with Mohammed, is just since my institute is an institute that might have interest for you guys, for the young generation, or those that are basically looking at the webinar or that will be looking at the webinar. I mean, there is a good side of the social networks is that this will be kept over some time on internet, and I think that it might become a little bit more useful, is to give a little bit of a hint of the programs that we have if there are students that might have interest in joining us. There's an application process, of course, there's a selection process. It's not as straightforward as you may think. And then later on, I will get you into very simple principles, or I will try to describe what I think is an earthquake scientist, okay? Myself, the way I view an earthquake scientist. This is outreach, so I guess that we have students that still do not clearly understand what is required to become an earthquake scientist that should be, on the long run, contributing to the society. And then I will take you into the science part that I will try to make as simple as possible. The science part will be represented by two different places in the world as well. I mean, there will be some theoretical aspects. I promise to not show any equation. There will be one equation in the beginning. And the idea is to take you to the Himalayas, because this is a fast deforming region. It's very fast. So we see things in all the beauties. I mean, Mother Nature is quite impressive there. And then I will take you to Italy. Italy is not a very fast deforming region. It's relatively moderate or even slow to some extent in some regions. I mean, it's almost the same rates of deformation that we have in our home country, which is Algeria. So let me get started, okay? And this is a picture that looks like, I mean, if without the damages, if you look at this picture prior to the earthquake, this is Italy. This is a little village in Amatrice that was destroyed by the earthquake in 2016. And it looks like a village Kabyle when you see it without the damages. So I hope that nothing of this sort will happen also to in our little villages in the mountains there. So before I get started, I would like really to give credit to a person. And this person is Asya Harbi. Asya is a seismologist. She was a research director at Prague, and she is a person that I know since 1993, actually, when I got, well, 1992 to tell the truth. I mean, and then since then we were in touch, and she was visiting ICTP for several months, and then she came here as visiting scientist, maybe something like more than 25 times, actually. And Asya is an outstanding fellow. She's both from the science viewpoint and also from the international cooperation viewpoint. So she's a historical seismologist, and then she was leading programs, and she was helping us here at ICTP build capacity. And she's very well known in all Northern African countries and all the Mediterranean countries. So she's a person that we will be missing, and I think that by giving credit to her, I know that Asya would not like to see me giving credit to her, But unfortunately, I mean, you know, now she will not say no. I mean, this is a big loss for us, and there are many Algerian women that are doing as great as Asia, and we look forward to see plenty of Asia Harbi. And she was a person that was fully dedicated to students. So this was quite this was amazing. I mean, she never had any hidden agenda, any personal issue on her work, but she was always focusing on for the interest of the students. So this said, I would like to get started, as Mohammed has asked me, just by giving you a little bit of a hint. I work for this ICTP, which is the International Center for Theoretical Physics. Do not worry by the name, okay? Do not be frightened by the name. And the name goes back to the inception of the center in 1964. But now it's broad science. There is earth science here. So we have a section on earth system physics. It's rooted to physics in the sense that you need to have a little bit of an analytical background, and you need to not be frightened by equations. But although this is more of physics, I mean, understanding the physics of the equations. So we support scientists from the graduate studies up to the senior level. So we have different programs. Look at the website of ICTP, then you will see that we have a diploma program that is intended to students that do have a physics background that would like to become a seismologist or high energy physicist or condensed matter physicist or mathematicians. And we have sandwich PhDs as well. I mean, for PhDs that are enrolled in Algeria that would like to work with us and spend up to 6 months per year at ICTP. And we have other programs that are more career development once you get your PhD, and then we know that you're very competitive in your field, then ICTP would give you a contract of 6 years, and you can come and stay with us for a month on a yearly basis and do your own research. So, now, this said, let me get to the earthquake business. If you are a student and you would like to become an earthquake scientist, these are the 3 elements that are requested. Okay, the first one is F equal ma. This is force equal mass per acceleration. This is an equation. Okay, this is the basic equation that we have in seismology. Okay, then you could make it as complicated as you wish. Okay, you could solve this equation in different ways. And you need to have a little bit of an analytical thinking. You need to understand, you need to play a little bit with equations, but what we ask is not that you have this mathematical background for nothing, but you get into the physics of the math and the physics of the equations, right? This is needed. And the second thing that is needed is, here it's written even in a way that the geologist would understand it, that in the sense that this is facious, I mean facious is faciès, and anything that we do has to be realistic. Geology is extremely important for us. I mean, if we physicists would like to model an earth process and we're not accounting for geological data sets, we're not doing good. An earthquake scientist is not a string theorist, okay? It's not theoretical physics in which it's oxygen for the brain and then it contributes to the fundamental science and so on and so forth. But you need to do realistic modeling because the next earthquake will be hitting down your models. And the third thing is that you need to be good in computer science. This is lsstar.out. Here you're listing your codes here, and you need to be good in computer science, reasonably good, but the main issue here is to combine the 3. To combine the 3, why? I'm not those heavy modelers that do models for the fun of doing models, but the model, because at the end of the day, if you would like to understand earth processes and you're building a model and then you have, at the end, you'll come out with 2 outputs, a model and the earth. You have two unknowns, which is the model and the earth, and you're not doing good. Then you will basically have a model that would not tell you much, and then you would increase your uncertainties. Then the solution to the problem here, if you build the model, is to account for geology, which is Mother Nature. Okay, these are direct data sets, direct observations. And the second is to understand the physics of those equations that you're solving in the computer. Because the earth speaks a language, and the language of the earth is called continuum mechanics. This is a mixture of fluid mechanics and elasticity. okay? Then if you know the physics of those equations that you're solving, then you would definitely have an intuition on whether your models are artifact or you're generating things that are just there because you're selling some complicated stuff, okay? So then if seismologists or the earthquake scientists that I like myself is a combination of these three different aspects. So let's get started. I think that seismology connects basically three different things. I mean, we have an earthquake that takes place, okay, on a source, and then it propagates through a medium, which is the path, and then it gets recorded by a seismic station, or it gets recorded by our buildings, or it gets recorded by human beings, right? And this part is called hazard, okay? Anything that works along these three different aspects, I mean, the source, the medium, and the effect at the surface is still hazard assessment, okay? And then when we involve the superstructures, which are the buildings, and then we are getting into engineering system, then we talk about risk, because here we should be including the damage or loss to society. Then if you are an earthquake geologist, and then you would like to, then you tell the, hey, I'm an earthquake geologist, and if you would like to become good in hazard analysis, then you need to provide an input within a time span of interest to the society. And what is the time span of interest to the society? It's just the lifetime of a building. So you need to bring down your geological time scales to the time scale of a building. Then geology becomes useful, okay? When geology becomes useful, this is extremely efficient, because I mean, these are extremely robust data sets, okay? So if you would like to do this, as I've shown in the beginning, then you have a combination of different, your background would require a combination of 4 different aspects. You may be a good theoretician and can handle good observations, but you will require to use computers nowadays, or you could use lab experiment. Then this is all the background that is required in earthquake sciences. At the same time, the sciences that we're using for earthquake hazard that do have a fundamental input to the hazard assessment or to risk are these ones. Then transdisciplinarity now is used by, now that I started working with social scientists, I learned that multidisciplinary is just multidisciplinary. It does not mean that the disciplines should be interconnected, but the right word to use here is transdisciplinary. It means that the fields should be basically one overlapping with the other one, right? And geodesy and seismology do overlap, and I think that now it's clear even in terms of observations, because with GPS we're getting to high rates, we're getting to sampling rates that are similar to the sampling rates of seismology. And seismology, when you get to long period content within your waveforms, you're getting to the static world, which is the geology. And then all this connects well to the engineers. The engineers should be doing it better. I think that the only, straight line here, the straight word that you see is engineering, because at the end of the day, engineers have to solve problems. We seismologists have to understand, okay? And we have to understand the processes and give inputs to the engineers to simulate the response of the buildings. So what is enabling nowadays earthquake progress in earthquake research? There are 2 different aspects. I think that we are at a level in which the fundamental theory is strong enough. Continuum mechanics is a respectable field in mathematics, in applied mathematics, okay? And we have enough theory. We're basically now in a stage where we're having plenty of data sets and new technologies, and we need more computational power. Okay, then computational power is becoming increasingly important if we would like to handle big data sets. Okay, and this is the new generation of computational seismologists, but that do have a theoretical background and that do need to understand geology. Because at the end of the day, if you build a model and then once you finish, the result of your model for you will be a little bit strange, then you're not solving any problem. You're not understanding the Earth. You'll have 2 unknowns, the Earth and the model, okay? And we need to be extremely careful. When we get into data sets, of course, Japan is always a place that we like very much. And then Algeria has to have respectable networks. We do have networks in Algeria, but we need always more data sets. We need more data both on the continental part and on the offshore part, within the sea, on the Mediterranean Sea. We have earthquakes along the shorelines, and these earthquakes are quite dangerous because they generate tsunamis. So once you have these huge data sets, you could do plenty of good things, okay? Interesting things. I do not recommend students to go and fetch programs and then do these fancy pictures without understanding the physics. You need to understand the physics if you would like to do a PhD in these specific fields. This is back projection that is used to look at large earthquakes like the Tohoku earthquake, and then on the base of this, you could look at the rupture and you could image the rupture with a high resolving power. Okay, and for this, you need dense seismic arrays. You could even use seismic arrays that are in the United States and in Japan and in Europe to look at an Algerian earthquake that is of magnitude 7.5 and plus. Let's hope that this will not happen. What next? And this is the wording for the senior scientists that are looking at us. I do not ask young scientists to get into this business. When you are a student, you need just to worry about your studies. When you go over 50, I'm over 50, but with very few years, then you need to get into maximizing the impact of research. Maximizing the impact of research means talking with policymakers. Because at the end of the day, I mean, you could talk with your engineer and then you give him the values of acceleration, design, ground acceleration, and all that stuff. But at the end of the day, it's the politics that will put the money. It's the politics that will set the rules. And policymakers, they are incapable of using research-based evidence. Not because these guys are bad, no, because it's not within their time span, okay? It's just not within their time span. Then senior scientists need to help us understand how to talk to policymakers. I start to believe that the problem of the communication between we scientists and policymaker, it's not because policymakers are not listening to us. So time to time, we scientists do not go with a single word. We do not find consensus. We keep fighting. And we cannot show to policymakers that we fight. But fighting in science is normal, right? I mean, when you go to congresses, you fight in a very kind way. You defend your own ideas and your own thinking with all due respect to your colleagues. And this is part of the science. This is the way science is growing. But if you go to a policymaker and then he sees two scientists that are speaking a different language, then he would think that, hey, here, I better go. So research evidence is based on a context that is quite free. We think freely. We do not have constraints, right? While a policymaker, it has to be a context, okay? And in science, anything that we call as an evidence has to be proved empirically. You do a theory, but if there is no experiments that demonstrate that one, then you're a sort of, this is shaky. The Nobel Prize winners are always empirically, I mean, the physics that is behind has been empirically proven. And then it has to be theoretically driven. Then you start from theory and then you start making your plans. And then as long as it takes, the time is, you know, when you do your PhD and then you finish it, then you could continue working on a specific subject for years, and then you would improve, and with rigor, you would have better results and so on and so forth. While a policymaker has time because he's voted for a certain period of time, and then either he does that part within his time span and he gets credit on what he does, otherwise it's arm waving. Okay, it's selling bananas in using a very simplistic word. And if you get a good policymaker, then you get into a process that is very complicated. I learned all this from social scientists. Social scientists do tell us, to seismologists, how to talk to policymakers. Once you've convinced your policymaker, then you get into the bureaucracy to get the law that is validated so that Algiers become, you know, of a certain level in terms of seismic hazard. So these are things that require time, and it's a completely different, I mean, different process than the ones that we're used to. Then if we have these ones in mind, then we could better talk to policymakers. Okay, then the other way around, talking to policy, talking to science, to social scientists, is that the science and policy discussion may be a little bit shaky. Okay, at some point we scientists give up. Okay, then if you would like to do it in a different way, then talk to the communities, because communities will be voting the policymakers. And then the communities would tell to the policymaker, hey, if you want my vote, I would like you to account for, you know, drought. I would like you to account for floods, for earthquakes in Algiers, right? And these are the ways of doing it. And then there is always this time scale, you know, no one would think that this would affect me, you know, an earthquake. I mean, when we got 1980 Al Asnam Sharif earthquake, I mean, we were all, you know, worried. And then after some time, the memory has faded. I mean, it disappeared, it ended up. So we forgot. So this is very bad. We need to avoid this. Let's get to the science. Then risk is equal to hazard that you multiply by the vulnerability and the exposure. Although I'm an engineer by background, I decided not to deal with that part. I think that Muhammad is an engineer. So myself, I talk about hazard, okay? And hazard is basically the questions that we try and answer. We seismologists, when it goes to hazard, is where the next earthquake will happen. Here I will be using the expression of Obama, okay? Obama in the good time. Yes, we can. We seismologists can tell. When I say seismologist, means that an earthquake scientist could be a geologist, a geodesist, an earthquake geodesist, or an earthquake seismologist. Then yes, we can. How big will be the next earthquake? Yes, we can. How often they happen? Yes, we can. These are three necessary ingredients to build up a hazard analysis. Okay, when it goes to when, this is earthquake prediction, not yet, I would say. Okay, this does not mean that I'm not a big fan of earthquake prediction, but I think that earthquake prediction is still at a research level. And we can't even show earthquake prediction to policymakers, because policymakers, if they know that you're a predictor, you're an earthquake predictor, then they would just tell you, hey, tell me just a few days before the earthquake happens, and then I will start evacuating. And you know, you could even know when the earthquake will happen, but trust me, first, you will not be able to evacuate. And second, you will never stop the earthquake. Then the buildings that should be there should be designed on a safety base. So let's continue the science here. This is a slide that looks a little bit complicated, but this is the slide, this is the end of the talk. Let's put it this way. I think that we've come a long way in monitoring and modeling earthquake deformation. Myself, I started working on earthquakes in 1991, 1992. Since then, I think that we've come in a very long way in modeling things and monitoring earthquakes. Okay. And then on one side, what you see here, okay, then you see basically plate A versus plate B. In between the two plates, there are faults that you see here. These are what we call right lateral strike slips, okay? Then these are end members of the deformation that you would expect at the plate boundary. If the plate boundary is made of these three faults, and the plates that are fighting one against the other one, this is one plate and this is the other plate, okay? If we look at them at the surface, we will have an understanding at the surface. We need to understand what is going on down inside the Earth structure, right? Here I'm splitting the Earth into what I call a schizosphere and what I call a plastosphere. Okay, these words mean very simplistically, schizosphere, it means that it's elastic. It will rupture. This is the place where you could get a rock, and then if you put it on your head, blood will come out. Don't do it. While if you go to the plastosphere, then these are places in which you would expect the Earth to behave in a time-dependent fashion. It becomes like plastic, right? And then it's viscous, viscoelastic. Let's use these very difficult words for a known seismologist. Then the plastosphere part should be the part in which the plate tectonics machine, the big machine that drives the deformation at the Earth level, would reach before it gets into the fault, right? Then the plastosphere would be the transition between the plate tectonics forces, which are the large regional forces, and the plastosphere should act as a sort of a wedge in which maybe deformation will be transferred to the faults. You have different models of faults when it goes to the structure of the Earth. You have faults that do shut down, they stop, at the interaction between your schistosphere and blastosphere. And you have the other end member is that faults are going down and they are sampling their own machine, their own engine. Okay, they are reaching the blastosphere and they are cutting the blastosphere, and they end up with wide shear zones, or they are single faults that are basically cutting two different mediums that do have two different rheological properties. Rheology, it means rigidity and viscosity. This is the way in between the two. Now, this is a plate boundary. Then the plate boundary, the ideal, this is a very conceptual scheme, is either you're looking at faults in Algeria that do have this scheme, or we have this scheme. We do not know yet in Algeria, unfortunately. I mean, Al-Aslam has provided us a big deal of information, but the post-seismic studies that would be allowing us to know whether the faults do sample the schistosphere, we were not able to do them, because in 1980 we didn't have GPS, and then the classical geodesy was not doing very fair. We were looking at viscoelastic relaxation. It's still a big question mark. Now, if we take one single fault within the plate boundary, because plate boundaries are made of different faults, one single fault, like one of these faults, is behaving in a completely different way. It responds to a continuous spectrum of deformation. It could either move in a very seismic fashion like an earthquake would do, okay, very fast, or it could be even very supersonic. This is what we call the super shear earthquake. The super shear earthquake, it's an earthquake that happens on a fault that rupture at a velocity that is over the shear wave velocity of the medium, right? Then the rupture velocity will go faster than the velocity of the medium. While a normal earthquake would be an earthquake that would happen at a velocity that is less than 80% of the shear wave velocity of the medium. At the same time, this same fault could generate all the spectrum up to what we call a seismic slip or creep events or slow earthquakes. And in this case, it would deform in a very time-dependent fashion. It would not generate seismic waves. It would not damage buildings. Okay, these are interesting events. These are called transients. Okay, and these transients, they add into the system, or they diminish, they take away strains from the system, and we need to understand them. Now, with the excellent GPS technology that we have, we're able to understand these transients. We're able to map them out. We're able to chase them. Okay, and I'll be talking about these aspects as well. So what is the earthquake cycle? Then it boils down to understanding what an earthquake cycle is. In 1992, when I started doing seismology, for me, there is basically a stress loading or a strain loading. By the way, we do not measure stresses in the earth. We model stresses. What we measure in the earth are displacements and strains, okay? And then you need a constitutive load to get your strains into stresses. Then what we see here, then you reach a certain threshold, and then you have an earthquake. Then this is time. This is an extremely simplistic model. And myself, I did rock mechanics when I was in Bab Zuwar. I'm very proud of my rock mechanics background. I always learned that samples in the lab, if you squeeze them, they would not rupture in a very steady state fashion, in a very linear fashion. They would exhibit a transitory primary creep, and they would end up with an accelerate. They would even reach an acceleration before the rupture. Okay, this is what rock mechanics is telling us. In fact, this old way of looking at the earthquake cycle now, we just forget about it. Okay, it doesn't work anymore. This is the way we view the earthquake cycle now. This is a paper coming from Giulio Di Toro, a good friend of mine that is in Padova here, close to Trieste. This was published in Nature, and this is the way we view the earthquake cycle. This is still time versus here the fault strength and the shear stresses. You see that we do not have lines, but we have really, a sort of a non-linearity in the beginning and then non-linearity in the end, which could be the beginning of the pre-seismic phase of an earthquake cycle. Then you see that the earthquake cycle, and the repetition of earthquakes is not is not periodic. I mean, there is no periodicity within the return period of earthquakes, okay? This does not mean that this is the most complicated case. This is, let's say, the fundamental way of looking at the earthquake cycle right now. And these transients, they are extremely important because they may change the budget of strains within a fault. They may accelerate its rupture or they may decelerate its rupture. Okay, and these are interesting things that we do and we would like to know. And this earthquake cycle here that you see is coming from rock mechanics experiments. These are basically experiments that are done with a rotary system, for those of you that do know, but they do get into seismic slip velocities. They are very reasonable. These are rock mechanics experiments. The space conditions are not very reasonable, but the velocities, the seismic rupture velocity is of the order of the same seismic rupture velocity, seismic slip velocity, which is the meters per second. Okay, here I'm not talking about a rupture front of an earthquake. Please do not mix up, which is kilometers per second. I'm talking about the velocity at which the slip is going to propagate on your fault. So this is what rock mechanics is telling us, but we don't want to do it. We don't want to solve the earth problem with rock mechanics. Rock mechanics is good in doing parametric analysis, in understanding, right? We would like to understand. We would like to understand which is the leading parameter within the experiment, which is the parameter that does not contribute at all, or which is the most critical parameter. And the most critical parameter in this specific case is called friction, right? So we can do this at the scale of a lithosphere, and this is what I call from the natural lab, which is where you do your experiments from the laboratory to the natural lab. And the natural lab here is a very nice picture, and this is coming from El Aslam. This is a picture by Mustafa Marawi that is well known in Algeria with all his contributions regarding active faulting studies in northern part of our country. And here you see a beautiful cut. When I went to the field with Mustafa to look at this fault, I was just, wow. We have such beautiful natural laboratory in Algeria, and myself as a student, I was not exposed to it. And this is a big shame. And I think that we need to sort this out. We need to learn out of these earthquakes. And Mustafa was taking students, but he was working at Prague, so I would like to see more university colleagues taking students to look at these faults, because these faults are just impressive. You see physics in real time. This is impressive. These are places that we cannot forget. We need to continue taking knowledge out of these places, okay? And this is also for due respect for those people that died following the earthquake. Then what I call a natural lab is that in the rock mechanics experiment, you use your triaxial or your rotary system to rupture the sample, while here you wait the earthquake to initiate your lithospheric scale rock mechanics experiment. Then what you do, you establish initially the geometry and the initial and boundary conditions, and here you could look at different fields, surface geology and geomorphology. You look at kinematic parameters of your faulting from geology. You do some earth structure through, I'm a big fan of surface wave tomography and nonlinear inversion. I'm not a body wave person, okay? And then don't ask me questions about body wave tomography. And you can take relevant deformation measurements at the same time. You look at the seismicity from the catalogs. If you have money, you could buy GPS. And if you have a brave earthquake geologist, do paleoseismology across the faults. And then you need to know the limits and the error bars of all these data sets that you're looking at, and use models to resolve your constitutive properties that would allow you to build up what we call a model of strain accumulation that may carry a predictive power for future stress patterns. But this does not mean that we will be predicting your earthquake. You will just come out with a model that would tell, hey, Boumerdès has ruptured here. Now, with all the knowledge that we gained out of this earthquake with the rock mechanics experiment that we've been running in Boumerdès, it would be nice now to know which are the faults that are on a high probability to rupture next. But this does not mean that even that fault will rupture, okay? Because stresses are not quantities that you could measure in the field, and because this is a very nonlinear field, and it's the equations that you're solving in the system are extremely complicated. So in here, I mean, what we've been showing with the earthquake cycle here, I was talking about the time. Then I'm plotting the time domain. I always tell to my student to think if you're basically receiving information during the class, try to put all this information into two main containers, the time domain and the space domain. And then there is another domain that we will discover later on, is the depth, because the Earth is a chunk, you know, it's thick. It's not something that is just the surface, right? You need to understand the Earth structure, and we will be talking about this. Then from time, let's go to space domain. This is space, okay? What you look at here, this is a fault. This is Umbria Marki in 1997. This is a fault that we've been modeling many years ago. This goes back to a paper by a former PhD student of mine that is associate professor in Delft now in 2008. And this is a fault, and this is the cool seismic deformation that you would expect from a fault with its length scales, okay? The length scales here are very tiny. I mean, you're looking at this line is telling you that this is 10-kilometer dip, and then this is 20 kilometer in total around the cool seismic deformation. And this is the cool seismic deformation. And if you have to design a GPS network to monitor your cool seismic deformation, you need to be close to the fault, but you need also to be a little bit far, but not that far away, not too far away. You need to sample at least the thickness of your seismogenic layers, so to see the decay of your displacement when you get far away from your fault. And then you need to be close enough to the fault to see even what we call, what engineers do call the fling. The fling is the static maximum displacement that you see within those strong motion waveforms. And these ones are terrific for buildings, okay? These are long period staff that may knock down a high-rise building. So, and then this is the cool seismic. Then the post-seismic, which is this one, it looks like a bird that has no head, okay? This is the surface of the Earth, using still the same scale. Here we're talking about different length scales. The length scales within the post-seismic are far, far bigger. Then don't do the same mistake that was done by some colleagues of mine in the old time that did not know the physics before getting into the field, okay? If you would like to measure deformation, the post-seismic deformation of a fault, do not sit on the fault itself, okay? You need to get far away from the fault so that you're able to sample the interaction between your elastic layer, which is this patch, okay, above the yellow line, and the viscoelastic patch that is beneath the yellow line, okay? And this is what physics is telling us. This is a very simple, you know, we're solving with the computer equations, and this is a clear understanding, and earthquakes do behave in this way. So the key point in all this, as I started my presentation, was to tell you, hey, I would like to know how the big strains are transferred to the fault. Then the post-seismic would definitely let you know whether your fault stops at the base here of your elastic layer, which is this one, or it continues down within your lower crust till it hits your uppermost mantle. It could have this geometry, or it could maybe end up in a sheared rock. This is what geologists and petrologists are good in looking at, and then you may find the deepest part of your fault ending up with a wide shear zone, and then you may find a fault that stops at the base of your elastic layer, and it stops completely. It shuts down, and then until you get into your viscoelastic rheology. So let's get started with a very general map. Okay, the very general map is the map of the seismicity of the world. Map of the seismicity of the world I show to my student, I tell them which is the first order information that you could extract out of this map. The first order information that I would see myself is that seismicity along the ocean, along the plate boundaries in the ocean, is extremely well localized, while the seismicity within the continents is broad. These are bad news, right, for earthquake hazard. Then the fish should be more safe than the humans, because the fish should know where the big transform faults are, or the big, you know, this big shear zones beneath the ocean are. Then you get far away from it, and then you could leave your life. While if you look at the Himalayas, for instance, here, the plate boundary goes over 1,000 kilometers of width, we still do not know how wide is the plate boundary in northern Algeria. No way, we do not know it, because we need to have plenty of stations and sections all across the northern part till the southern part to see how the strains are changing, whether they are shutting down when we're getting close to the Atlas Sahara, and then this does not stop here. We need to know the Earth structure, as I will be showing it to you. And the plate boundaries within the ocean that are represented in red do behave differently than those ones in the continents. And this makes our life very difficult in terms of earthquake hazard. This is plate tectonics. So the fundamental tenet of plate tectonics is that the surface of the Earth is split into a small number of rigid plates whose relative motions are taken up at the narrow bands around their edges. And this is exactly what you see. This is your African plate. And then you see that all the deformation is basically located at the edges. And if you'd like to see how this plate is moving, you just need to use a very, very basic equation. And the governing equation is the governing equation of plate tectonics, which is V equal omega R. Okay, then your angular velocity here, and that you need to multiply by your R, okay, that is your axis that is passing through the center of the Earth, right? So this is the physics behind the tenet of plate tectonics, which is the Euler's fixed point theory. If you would like to know the motion between two plates, the relative motion between two plates, then motion of plate A versus motion plate B, then it could be described by the rotation about the vertical axe around A and the vertical axe around B, and the relative motion will be the difference between the two. As simple as it is. And it could end up with a clockwise rotation or an anti-clockwise rotation. But there's always a but with plate tectonics. Plate tectonics does not seem to work correct within the continents. Why? It works fine within the oceans, in which we have the localized deformation schemes, because we seismologists, every time there is a large earthquake that takes place, we know the slip vector of that earthquake. And then if we take that vector field from the earthquake focal solution and compare it to the motion of the surrounding plates, they coincide. In the oceans, they tend to coincide, okay? While if you do this in the continent, it may not be the case. Then if you focus at a regional level here, and here we're looking at the Alpine Himalayan belt here, and then getting into Indonesia where the seismicity is extremely broad, and we will focus on the Himalayan region. I think that what you're looking here, this is India pushing, and this is Eurasia, and all this is a plate boundary in which we have very large earthquakes. And these beach balls that are football balls, for those of you that do not know what these ones are, these are basically balls that we use in seismology to make the non-seismologist ignorant. Okay, so I mean the blue ones are telling you that the Earth is squeezing. The red ones is telling you that the Earth is opening. So how can you get a context in which India is pushing Eurasia, at the same time you have coexistence of compression and extension? These are earthquakes. Earthquakes, they seem to be well distributed where the topography is high. And this is a good point. But the strains here do not reflect very well the topography to some extent, because if you go to Tibet, Tibet is very, very high, but it's extending at the same time. And if we use another proxy like GPS, GPS would tell us this is the motion of India, and then look at the GPS velocity field here. It's not a GPS velocity field that will end in decay when you get far away from the pusher, from India that is pushing. And it has a completely funny and different geometry when you go towards the Indochina part here, okay? Then there is a sort of escape. And here there is a complete decrease, and then it restarts again, right? So if you use plate tectonics, this is not the velocity field that you would be able to reconstruct. This does not happen only in India or in the Himalayas. It happens in Greece, as well. I mean, this is an example from Greece where the velocity field does not reflect the motion of Africa versus Eurasia. It's a very difficult velocity field, okay? And it works also in the Middle East. This is Iran, okay, where you have the plate boundary is not reflecting the motion of the big plates, okay? Then continental deformation tend to behave in a very different way. Then you can't use plate tectonics to understand earthquake hazard, okay? And you need to use something different, and you need to be extremely careful. This applies to the United States. This is the San Andreas. This plate is basically sliding in a transform fashion. This is the Pacific versus the North American plate. And here you have the basin and range that is going an extension. And we know why now. We know why the basin and range is extending, having nearby the San Andreas. So the take-home points is that the morphology of the plate boundaries do exhibit significant contrast in elevation, and these occur over length scales of 100 to 1,000 of kilometers. It could be 100 kilometers in Algeria. It could be more. It's more than 1,000 kilometers in the Himalayas. If you look at the thicknesses of your crust, which is the first chunk of the earth that is beneath your feet, then it is completely variable. It changes from 35 to 60 to 70 kilometers. And the seismic activity does coincide with the topographic relief, but the mechanisms, the active strain rates that are induced by earthquakes do not reflect the finite strain rates. Okay, and there are significant velocity differences within these zones. If there are changes within the velocity field, then you can't do it with plate tectonics. Then this plate tectonics scheme does not work, because we would have reconstructed the velocity field that looks like this one, just a decay, a full decay of the velocity field, and this is quite well known. Now, which is completely different from the one that you have here. Now, let's get to seismicity in the Himalayas. If you are an earthquake hazard analyst, there are earthquake hazard analysts that like playing only with seismicity. This is bad news. I think that this is bad news, even though we're working in a place like the Himalayas, because the Himalayas are fast. This is centimeters per year of deformation. Then you would think that even an earthquake catalog of more than 100 years would be representative of the deformation. It's not. And I will show you this in a minute. Okay, then unless you use geological data sets or historical data sets to have a full picture, otherwise your hazard maps will be definitely sooner or later knocked down by the first earthquake that will hit the region. So if you look at the Himalayas, this is the front line where we have magnitude 7.5 and plus, these huge, large magnitude earthquakes. And all these large magnitude earthquakes, they happen to happen at the edge of the Himalayas. So this is the topography. This is India. This is the Himalayas. This is Tibet. Then it's a section that goes across the Himalaya, okay? And these are basically the frontal parts of these big décollements. And this is where the place where we see the little seismicity that you see over even 100 years. So if you think that you're doing earthquake hazard by looking at the seismicity here, while your large earthquakes are popping up at the end, then you're doing wrong. Then you need to be careful. In other words, in the Himalayas, the strain is accumulating here, which is the transition between your elastic part and your little bit of more time-dependent way of loading up, and the record of strain release that is here. And now we have an evidence in the Himalaya that there was a magnitude 8.9 and plus. Okay, these are the original models of Roger Bilham. If you take India pushing, this is the Himalayas, and this is the Tibetan Plateau, and this is the part of your system that is basically taking the strains from the plate tectonics, and then you run this in a time-dependent fashion with a velocity of 1.8 meters per century, per 100 years. And these are the GPS measurements that indicate that the process of deformation in the Himalaya is elastic and is focused around the locked line. It's a locked line that is at the southern edge of the Tibetan Plateau. This is the north and this is the south. Then the locked part is here. It's between the Himalaya and the leading edge, okay? Then north of which India is creeping slowly downward and northward, okay? It dives beneath the Tibetan plateau. And if you load it up over time and you start building up your Himalayas, okay? And then at some point, friction will basically collapse because the elastic restoring forces will be over. And then the key to the size of future earthquake in the Himalaya is definitely the elapsed time since the last earthquake. Then what happens here is that when a critical stress is reached, an earthquake drives the Himalaya southward over the northward descending Indian plate, right? Then you could have earthquakes in the region. You could have earthquakes in the region here these are the different scenarios that you could come out with. These are scenarios that were expressed already by Roger many years ago. I think this goes back to 2005. You could get magnitude 7.8 earthquake with a fault that is popping up far away from the leading edge, which is the Valley of Kashmir here. And here you're ending up with a 7.8 moment magnitude, or this would lead at the main boundary thrust with an 8.5, or you could rupture the whole décollement beneath the Himalayas up to the Indian part and end up with an M max of 8.9. The bad news is that it seems like this has happened. And this is the evidence from Steve Wisniewski. Steve Wisniewski is this gentleman that you see here. Steve happens to be a good paleoseismologist, but at the same time, he's a good earthquake physicist. He's someone that has worked a big deal on B values versus characteristic earthquake. And here you see a fault scarp that has more than 20 meters of displacement. And more than 20 meters of displacement should be around the magnitude 8.9. So if you have this information, you're still missing the knowledge of the Earth structure. The Earth structure becomes extremely important in understanding the physics of the processes here, why this is taking place and how this is taking place. This is what we did with a former postdoc of mine. This is Naresh Kumar, that is now a principal scientist in the Wadia Himalayan Institute in Dehradun. Naresh has deployed a very big broadband network of stations across close to the syntax of the Himalayas, and we started looking at the Earth structure beneath the Himalayas from the leading edge, getting close and then crossing what we call the Karakoram fault, for those of you that know the region. And we wanted to look at the structure of the Earth within this chain of the Himalaya, right? Then we used different methods. I can tell you more about the methods if you're interested, but maybe in a separate discussion. And this is what we came out with. This is a section that goes from India and crosses the Himalaya and then ends up in a Tarim basin here, okay? And then what we see here is this fantastic velocity profile. This is like a geological cross-section, but from 0 to 80 kilometers. Here, we're not representing the lithologies, but we're representing the physical properties of the geology. Okay, these are seismic waves, and specifically, these are shear waves. This is a VS model. The VS model is telling us that beneath the Himalayas, within the crust, we have a low velocity that is trapped in between two high velocity bodies. Green is higher velocity. This is 3.5 and above, and yellow is less than 3.1. If you look at this picture, it looks like the head of a crocodile. It looks exactly like the head of a crocodile. And the low velocity is trapped in between. This is the resolution that we could reach prior to, because when you have, this was done using ambient noise, okay, then there was no large earthquake in the area, then we were just using normal or classical seismic tomography and together coupled with ambient noise. At the same time, if you look at the parallel section, but this time along this huge Karakoram fault, the Karakoram fault has been subject of long discussions with different groups, the French groups and the American groups, on its slip rates and so on and so forth. We've discovered that Karakoram is completely variable along strike. It seems that in the eastern part, the Karakoram is coupled to the uppermost mantle. There is no low velocity here. Then your crust is moving to your uppermost mantle, while here the Karakoram is connected to a very low velocity uppermost mantle. So this would have a significance also in terms of its loading processes or seismogenic potential, if someone wishes to put it in this way. If you compare the Himalaya Tibet, which is a very long, very large length scale with very fast deformation rates, to the European Alps, which is almost the same geology, okay, then it looks like it's the same thing. This is the crocodile model that we found out in a paper that we published together with Naresh in the Geological Society of London. And if we compare this to another work along the Transalp in the Alps, and this was published in 2002 in GRL, we see also a sort of a crocodile model. In the Alps, we had two models, either a crocodile model or lateral extrusion model, although they were very supportive of the crocodile model. So this crocodile model was done on the base of seismic profiles, while this one is done on the base of seismic tomography. Here we're reconciling a little bit the European Alps with the Himalayas. It seems like the deformation, although, I mean, in Europe, the Alps are straining at really, really slow values, millimeters to even less than millimeters in some specific places. Then came the Gorkha earthquake in the Himalaya. In Nepal, we were present before the earthquake, and we were present after the earthquake. My role is to build capacity. Then we were running workshops in schools prior to the 2015 Gorkha earthquake, and I was training 3 diploma students that became seismologists, full trained PhD seismologists. And even it happened to us within the Earthquake Without Frontier projects, in which that was led by Cambridge, to be there 2 weeks prior to the Gorkha earthquake. And we were running really a resilience show in the streets of Kathmandu. And then the earthquake took place. We went immediately right after with deployed GPS instruments, and together with the University of Cambridge, there were 36 broadband stations that were deployed. And there was a large collaborative effort involving ICTP and UNAVCO and different universities in the US and in the UK. And then some of our former diploma students that finished their PhDs abroad, this is specifically Surya Pashai, that was at the Australian National University. He came back to ICTP as a postdoc working on all this huge amount of data sets that we were gaining. And I will show you a few results. And Gorkha came in a place, this is a map, state of the art in terms of seismic budget, that was published by Roger Bilham in 2005, that was showing gaps in which places in which gaps, be careful in the way you use this word, or places in which there was less strain that was released compared to others. And Gorkha happened exactly here, in a place that seemed to be in need of an earthquake. Then this earthquake was a little bit overdue, but it took place as a 7.8, not as a magnitude 8.9 and plus. What we did at that time, we deployed GPS instruments, and this is the rupture that we dropped over the Himalaya of the earthquake, okay? And then we were chasing the post-seismic deformation. So these are all continuous GPS stations, and this is the strains that were basically the time-dependent strains that are after slip. After slip is basically a slip that happens on the décollement after the earthquake in a time-dependent fashion. We had very large after slip that was taking place on the northern part of the décollement, then at a larger depth, then towards the northern part of the Himalayas, then from the Everest, Mount Everest up to Tibet. But we had a full shutdown, you see here, while here to the north, I mean, the after slip was very high with an exponential decay, while to the north here, where the décollement was leading to the main frontal thrust, there was full locking. So these are bad news. At least within these 6 months right after the earthquake, we had an evidence of locking of the part that is towards the northern part. Okay, then I will get you back to a section so you could understand. Okay, this is exactly this. Then the earthquake took place on something similar to this, but the post-seismic did not move this part. Okay, then this is locked. If it's locked, then this is bad news. Okay, it means that it's not releasing strains. Okay, then it might be loading. There is a picture here. I'm sorry. So then the picture, this paper was published in Nature Geoscience. I mean, we published this paper it's in Nature Geoscience. Then what happened is that the after slip was telling us that we had very high values here, and this is the cool seismic rupture, and we had very small values when you get close to the leading edge, with no values at all along the leading edge. These are bad news. Okay. So what we did with the broadband, with the GPS, this is the work that we did, and then with the seismology, we started looking at the Earth structure beneath all the rupture area. This was a very, very international collaboration, and with the network is quite impressive. And a PhD student of mine that is finishing in a 2 weeks' time will be defending his thesis and using all these stations. What we discovered then here, we're basically scanning the Earth structure beneath all the rupture of Gorka and then following it up. And then here, this is like a geological cross-section. It's impressive what you can get. High resolution, then very high resolution data sets are giving you very high resolution results. And here you see the décollement beneath the Himalayas till the leading edge, and this is the epicenter of your earthquake. These are a number of sections that are perpendicular to the rupture. Then we could look at the heterogeneities and how the Earth structure was controlling the evolution of the rupture. And these are details that I will not be talking to you about today. Okay, and the most important result that we succeed to have is that the aftershocks that were happening in a place where there was a ramp inside the region that went co-seismically. There's a ramp here, and this ramp has ruptured in a very duplex fashion. This is what geologists call a duplex model, in which you have parallel faults that are basically linked to a décollement. This is exactly what we see, and it happens that this duplex happens to be a very low velocity in between two high velocities. And then if you plot here the rupture extent, you see that the tip of the rupture extent ends up in a very low velocity mid-crustal layer. And this low velocity mid-crustal layer is the place in which the big strains were accumulating over time till it has been transferred on the fault itself. So this is the way seismic tomography helps you understand the seismogenesis. And now we have ways of doing this without waiting for an earthquake. And this is exactly what should be done in different places in Northern Africa. We hope that this would happen. Now, if I take you to Italy, where Mohammed, then you let me know. I mean, I will just go fast over a few slides and then I will stop. Do I
take your time? No problem. Yeah, don't worry about time.
Continue.
Please take your time. Yeah.
Okay. Then, if I take you to Italy, Italy is a completely different setting. It's more complicated because the rates are slower and the space domains over which the deformation is taking place are shorter. Then, if your space boundary conditions are shorter, even the space boundary conditions, including what we call the geodynamics, is completely squeezed, then the knowledge of the Earth structure is badly needed. Okay, then this is what we call the Calabrian Arc. This is North Africa. This is Tunisia. This is called Nubia. Okay, this is Tunisia here, the plate boundary. And here we hit the Calabrian Arc, which is a subduction zone. And the plate boundary goes all along the peninsula. And then here is the Alps, and this is the place where we'll leave. Trieste is right here, and this is the dynamic chain. This is another plate boundary where we have earthquakes. And the interpretation that was given is that this finger here, which is called Adria, okay, is basically rotating anti-clockwise, opening the Italian peninsula on the left and closing up the Dinarides on the right. So this is kinematics. Okay, this is geometry. This is the Euler theorem. Exactly what I've been showing to you. This is plate tectonics. So then it seems like the interpretation is this. Then when we started having GPS data sets, we started observing different things. And if you look at the seismicity here, of course, the seismicity along the Italian peninsula is broadly distributed along the top of the chain here, but the width is not as big as the Himalayas. These are a few kilometers. It's 50-kilometer width, okay? And then at the same time, we do have earthquakes on the other part, but we have still few earthquakes inside what is assumed to be a rigid plate that is rotating anti-clockwise. So this is a map of the seismicity, and the seismicity is even showing inside the Adriatic Sea that there is a little bit of seismicity. Then this goes against the assumption that Adria is rigid. It seems that Adria is not rigid. So with the GPS data sets, then people started arguing now that Adria is maybe rigid, but it's made of two microplates. Let's divide the big plate, the big microplate, into two other smaller microplates. And I think that more GPS data sets we would have, and more smaller and tinier microplates we would get. Then it's in this context, it's clear that you need to image the Earth structure. There is no way out. If you do not image the Earth structure, then the GPS analysis that you're doing will be biased. You do not know where your GPS sites are sitting and whether those sites are sampling the long wavelength deformation that maybe changes within the your lithospheric thicknesses would appear. So this is Omori. It's known for seismologists. This is the Omori law for aftershocks that he visited Italy in 1908 when the earthquake took place. This is the plate boundary with all the historical earthquake, and this is a paper by Omori. And all the earthquakes that took place, even in Italy later on, came and filled the gaps, okay? And if you look at the GPS strain field, these are GPS vectors, then you would see that the central part, the largely strained area, is here. But we miss GPS stations on the other side, and which is ex-Yugoslavia. We did some works here in this gap that did not move yet, and this is called the Palino region. And paleoseismology has exhibited the existence of a fault that is very, very active, but did not move since thousands of years. When I finished my PhD, then in my second postdoc, I deployed GPS instrument across this fault, and we published a paper where we've shown that the GPS data sets were showing velocities of motion of this, the slip rate along this fault, were 4 times the trenching data sets. This was a transient. We were catching up a transient. So the GPS are completely different from we think that we were catching a transient. So in this context of the Mediterranean, and you need to worry, because what you look at, I mean, the GPS values that you see in Italy are far smaller than the GPS values that you have here in Greece, in the Hellenic Arc. Then we think that big part of this deformation would be controlled mainly not by external forces only, like Greece, where we have the subduction zone here that is very active, with large earthquakes taking place along the Hellenic Arc, while here there are no more large earthquakes along the subduction. The subduction here seems to be dead, okay? And even here, then it's, I mean, the knowledge of the Earth structure is badly needed. So with 2 PhD students, we X-rayed the area. These are the different rays, and we covered all this area, and we looked at the Earth structure. We looked at the Tyrrhenian, and we looked at Adria. These 2 PhD studies, I mean, one was done by a former PhD student of mine. He is Manu Marfu Daniel. He's from Ghana, and now he's doing a postdoc. And the second part was done by an Algerian student that is now a doctor. She's not a student anymore, and she's working at Prague, and her name is Radia Kharshoush. She did an excellent job. So what we did is that we looked at the Earth structure, but before doing this work, many years ago, a former student of mine and myself, I was looking at the structure across the Apennines here, and we discovered that the lithosphere structure is completely different from a normal one. You see that you move from the western part of the peninsula to the eastern part with very large changes within the thicknesses of your lithosphere. And then if you put a viscosity model here, you would get what we call delamination. Delamination is when you're piling away your lithosphere away from your crust. And this was explaining the existence even of dipper seismicity, intermediate depth seismicity that was taking place between 50 and 100 kilometers. This is an exciting paper that was reviewed by very top guns in seismology like Dan McKenzie and Peter Molnar and Greg Hausman. This has shown the importance of what we call in seismology body forces. These are buoyancy forces. These are not plate tectonics forces. And then with these models, we started chasing also the post-seismic deformation in order to have a very reasonable viscosity model. This viscosity model is connected to all the post-seismic deformation measurements that we were doing. Then with the students, we started looking at the Earth structure. We demonstrated that beneath the Tyrrhenian, the mantle was very close to the surface. Then we think that the mantle was completely exhumed beneath the Tyrrhenian. And then using fluid mechanics, this is a paper that we published in Nature, and we used basically a model in which we looked at the flow, and here you could see that there is a sort of an uplift of your asthenosphere getting into the Vavilov Basin, in which we have the largest volcano in Europe, the largest ocean bottom volcano that we have in Europe. So the knowledge of the Earth structure helps understanding the plate boundaries. While in Adria, this is the work of Radia, we've demonstrated by looking at this is a cross-section across what was considered as a very rigid plate. We demonstrated that it's not, the thicknesses were not continuous. Then the thicknesses were completely different, and there is a change of thicknesses of the lithosphere exactly where there is a very big topographic offset within the submarine topography, within the bathymetry. And this change within the bathymetry is reflected within the thickness of the lithosphere, where it changes from 90 kilometers to 160 kilometers, as well as in the thicknesses of the moho, where the moho is changing, the crust is changing from very shallow values to the south to bigger values to the north. Then systematically running also the same model, the same fluid mechanics model, this is buoyancy flow, we were able to fit the GPS, these are the observed GPS, with the model by just using body forces within the system. I think that with this, maybe we're a little bit running late. I had something else to talk about, which are transients, and this is a very nice paper for those of you that are expert to look at, in which we were chasing transients in the Apennines, following also the 2016 earthquake, and this is a very fresh of publication, where we've shown that transients within continental region have this ability of changing the strains and also leading to a far larger earthquakes within the system like L'Aquila. I think that I will stop here. We've gone over more than 1 hour. I have more slides, but I think that it's better that I stop here and take up questions.
Okay, thank you very much, Professor Abdelkrim, for your very insightful presentation and very generous presentation, because you really covered a very broad spectrum of topics here, from the politics behind the scientist, how the scientist should think or should act, as a technician, or how to tackle with political issues, down to very, very detailed discussions of the boundary deformations from Nepal to the North African case in Italy. So now I think it's time for the Q&A session. We still have some time for some questions. I would take some questions. So you can guys from YouTube or from Facebook, you can post your questions in the comments section.
That's a big frustration to know that there are maybe questions, but we do not know who are the people that are asked. Well, I mean, I can't see the faces anyway, but it's
Yes,
nice.
welcome to the virtual world. We cannot really know who's typing.
We're very tired
So,
of this.
yeah. All right, so let me just pick the first questions from Amin. He says, how big are the data set you cited, number of samples, size, and how good machine learning techniques apply to predicting post-seismic deformations? So maybe some words about the state of the art of the recent AI role on prediction of the deformations.
Ooh, that's interesting. Well, big data sets are, yes. I mean, the big data that we have now, I mean, I think that in seismology now we need to be a little bit more careful, because I have a colleague of mine who is a math person that works on machine learning, and he's someone that looks at the theory behind machine learning. You need to be a little bit, and he's extremely critical when you go to very, very extremely large amount of data sets, because I mean, at some point maybe you would see some artifacts. But machine learning is definitely a big solution to many problems, because we have such a big pool of data sets. And I think that at some point, data will be giving us information that physics will not be able even to clarify to some extent. And there has to be, I think that in the beginning, I would always advice to keep a trade-off between what physics is telling us and what the machine learning is telling us, right? There's a big use of machine learning now in earthquake detection. This is something that we're using here at ICTP. We've been using what we call template matching in the beginning, and then now we're getting into machine learning, picking the phases and so on and so forth. And this reveals to be extremely powerful. Getting into post-seismic studies, I don't think that we're having still a huge amount of data sets. We are having a huge amount of data sets in terms of aftershocks, but not in terms of GPS. Well, aftershocks, I think that the science of aftershocks has grown, and there is not a huge change within what we've been learning in the past. While the big learning difference that we're getting now is coming from these high-rate GPS. But we're still, I mean, the number of GPS stations is not as big as, it's not, I guess that geodetic data sets will maybe, well, I don't know whether I would put them within the big data scheme right now. Maybe this would come out with the huge Earthscope observatories. And now the advice that we give always is to co-locate your GPS instrument with your strong motion instrument and your broadband instrument, and then have them co-located in the same site, so you could compare and then have a more constraint to your observations. But machine learning is definitely a way forward. I'm very optimistic, but I don't think that myself I will be the person that will solve this problem. My students will, but I think that this goes a little bit beyond I still will stick to physics. At least up to now.
Yeah, thanks. Yeah, definitely. It's a big hot topic right now, even in engineering seismology. Probably they can bring a lot of plus to the prediction, earthquake prediction.
Yes,
Deformation. All right, so I will pick up. So again, if you have any questions on YouTube or here in Facebook, you can ask your question in the comment section, and then we will pick up. I will take the next questions from Ahmed. He says, if we succeeded to reproduce this in Nepal, probably he's talking about the case study, a very interesting result you presented about tomography, with very few stations, probably seismic stations, then it will be possible to do similar work for North Africa?
Of course. Yeah. I mean, it will be definitely possible to do anything. You just need, I think that there are reasonable networks in Algeria, and I think that these types of works could be easily done. And myself, I'm not working on Northern Africa. I mean, I stopped working on Northern Africa since the year 2000. Maybe my last paper goes back to the year 2000, and I apologize for not having maybe produced a little bit more papers, but I know that there are people that are working on North Africa. But maybe North Africa needs a little bit more networks, more data sets, more commitment, more open data policy, I would say. But of course, the open data policy has to be open. I mean, inside the country, at least to the local scientists, that we would see more papers popping up and more collaborations. So definitely the work that we did, definitely the work that we did in Nepal could be definitely done in Algeria, and the work that we did in Italy could be done in Algeria. Right. I mean, I just finished a meeting beforehand talking with, this was a big meeting about international collaboration that was organized by UNAVCO and IRIS. UNAVCO is it's an instrumental consortium for GPS instruments in the United States, and IRIS is the same. They have international stations. They put even stations at the international level, and I'm sure that there is a possibility to get many stations in Algeria. I mean, there has to be a willingness. There has to be. This gets beyond a little bit the science.
Okay, so it's more about about the problem of data openness, I would say, rather than a technical issue, right?
Well, I think that this is a touchy subject. Myself, I have really no time to get to it. But yes, anything that has been produced in different places. I mean, you know, when we run experiments in specific regions, because we have an idea. I mean, you submit a proposal and then you get funded, or your proposal is rejected. Okay, then in general, in the proposal, you have already ideas and on what you should be looking at, without having a bias, of course. I mean, you do not need to be biased, and then you do the work. While country-wise, I think that there are institutions like CRAG, like the National Institute of Geophysics, that do have stations that are used for monitoring, but that could even serve the science part independent of the earthquake sequences. It's always good to work to do science in a peaceful time. Okay, and now seismology, the methodology in seismology has grown enough to work with noise. You know, in the old time, we were removing noise from the seismograms, but now we're not removing the noise; we're using it. Right?
H over V, you know,
this is exactly what is going on. So I think that if you have a network that has been running for a year time, I think that with that network, you should be able to produce lithospheric scale cross sections across all Northern Africa from A to Z. There's no doubt.
Thank you very much for your answer. We pick up the next question from Yahya Muhammad again. Yahya Muhammadi, again, you can ask your questions in the comment section, rather in YouTube or here in Facebook. So the earthquake cycle model, is it applied to moderate 5-6 earthquake, which don't have a predictable or co-seismic deformation?
Well, I mean, you know, an earthquake, a moderate size earthquake has a co-seismic deformation. I mean, they are a little bit smaller. Then it depends on the instruments that you have. If your instruments are very close to magnitude 5 or magnitude 6, you could catch them. I mean, in Italy, we've been working with plenty of magnitude 6. And it's always good to work with moderate size earthquakes for one obvious reason, because they are more frequent in time and they have less noise, if you wish. A big earthquake, a magnitude 7 is, you know, it's a big machine. I mean, it's something huge that goes on, and then it will generate plenty of aftershocks. And while a moderate sized earthquake tend to decay very fast, so you require a little bit less time than a magnitude 7, and you can get many more papers. I mean, it's so use moderate sized earthquake and work on them. The earthquake cycle can apply even to magnitude 1. The physics is the same. Of course, when we talk about small earthquakes, okay, then I think that the discovery that was made following Sumatra earthquake, Sumatra is a magnitude 9.3, 9.4. That earthquake has brought us to length scales that were unique. I mean, we discovered that it's not as big as Alaska, as Chile in 1960, but it's smaller, but it had a rupture size that was far bigger, because the rupture has progressed from in an elastic fashion, and then it ended up in a patch that was moving with a slower seismic slip. So smaller earthquakes are important. We need to use them. It depends on the monitoring system or on the stations that you have.
Thank you very much, Professor, for your answer. So yeah, before I will have one personal last questions to close the Q&A session. Personally, I work a lot with magnetic and gravitic data inversion, especially satellite open source data, where we can have open source data for gravity and then try to run a blind inversion where you can have density distribution of the underneath structure. So this is actually commonly used in oil and gas exploration as well as for tectonic studies. So what do you think about these kind of passive or non-seismic methods for mapping?
Oh yeah, well, magnetotellurics is very, very good. I mean, specifically now we're involved in projects in East African Rift, where magnetotellurics is even stronger and more powerful to some extent than other classical seismological tools. But I'm a very transdisciplinary person. I'm a very multidisciplinary, but I think that my career now has reached the point where I will not be able to develop my magnetotelluric knowledge. So I trust on other investigators, but I'm not an expert in the field. But I know that, I mean, if we compare our seismic tomography results with what is coming out of the more potential methods, I think that it's giving very, very interesting results. I think, yeah, the future is there, but it has been, I mean, used heavily. At least Americans do it quite in a very, while we Europeans, I mean, in Europe, I mean, it's less used. I think that the use of magnetotelluric and seismology is less. It's more efficient maybe in volcanic systems. I don't know.
Yeah, especially some people are already talking about joint inversion between seismic and magnetic, doing some kind of joint inversion. You know.
Yeah, that's cute. Yeah, this is very cute. But I know the joint inversion from a theoretical viewpoint, but I'm not a big consumer of magnetotelluric data sets. Then I need to study. I have to study magnetotellurics, but I don't think that I will do it soon. But this is extremely important because plenty of people are doing it. People that I do respect are doing it.
Okay, so thank you very much, Professor Abdelkrim.
Thank you so much.
Very, very interesting webinar. It was a real pleasure to have you. We learned a lot during this 1 hour already, 1 hour and a half. So again, I will try to switch to Arabic a little bit. Donc, le projet هذا اللي رانا نخدموا فيه, comme on vous a déjà expliqué, on essaie d'inviter chaque mois un spécialiste dans le domaine des earthquake science, la sismologie et le parasismique, afin de démystifier cette science parce que ça reste une black box. We go to our seminars, we do our conferences, but we don't really share with the public. So I think it's really time to start preparing the population for the next big earthquake in Algeria. So that's why we are trying to promote this kind of webinars. Thank you very much again, Professor, for joining us. Donc, j'essaie aussi de dire juste un dernier mot. Je sais qu'en ce moment, des moments très difficiles en Algérie, en ce moment, very hard times, you know, especially with the COVID, with the lack of oxygen. And now we are starting with fire forest. C'est une grande perte pour toute l'Algérie.
Nous, on a perdu nos oliviers, malheureusement. Et puis, il y a des gens qui sont en Kabylie.
But what we have to do, what we can do is, what we are doing now in earthquake prediction is trying to prepare the population for the next earthquake. We are trying to do a background work on the population. نقدروا أيضا مع إناس to do the same work for the fire forest, because now it's starting to be a national point. It's getting serious,
you know. It is, yes. With climate change as well. With climate change, these are things that will come back again.
Climate change, you know, many people are working on this field to do something similar to what we are doing in earthquake.
Absolutely.
Invite people, explain why we have fire forest, why the climate is changing, what we need to do to prepare the population. This is a background that's really need to be done, not only earthquakes. صح كاين le problème تاع les séismes, on essaie de faire de notre mieux, ولكن كاين le problème تاع les fire forest أيضا نحاول إن شاء الله on essaie d'inviter, enfin, even if there are any specialists listening to this webinar, feel free to contact us and we can really start a project in this direction. With that said, Inshallah, ce mois-ci, on a 2 webinars. Donc, Professor Abdelkrim, Inshallah, next week we will have another presentation, another webinar. We will invite a Japanese professor, Dr. Masumi Yamada. She will introduce about the technology behind the Japanese earthquake early warning system. Wow. What's the algorithms behind it? How does it work? Can we implement something similar in Algeria with our know-how? So it will be very interesting, similar next week, inshallah, next Friday at 10 a.m. if I'm not wrong. Please check the INAS webpage. I think with that said, let me just invite Amin. Any final words, Amin, before closing this very interesting webinar?
نعم شكرا. نظن باللي صايرك هضرت على كل شيء. دونك الاسبوع القادم كاين ويبينار، جوج تاع الويبينارز، واحد تاع الجيو ساينس مع اللي هضرت عليه دروك. دونك جو كونفيرم اتس 10 AM 10 تاع الصباح في توقيت الجزائر نهار الجمعه. واليوم السبت كاين ويبينار اخر مع الاستاذ بقاسم حبه يهضر على فورت اندرشن ريفولوشن. دونك كيما مداري عندنا دو ويبينار في الويكاند اجوشل. دونك شكرا جزيلا. نعاود نرد لك.
يعطيك الصحة Amin. Again, thank you very much, and we thank also Professor Abdelkrim for his time, especially for a busy day he had today. So again, thank you very much, Professor, for your very valuable seminar we had right now.
Merci beaucoup. Merci.
Thank you, and looking forward to seeing you next
congratulations for what you do. This is very good.
يعطيك الصحة, Professor, and see you soon, hopefully. Thanks.
Thanks, Amin. Thanks.
The International Network of Algerian Scientists, INAS, is a non-profit organization founded in 2016 by Algerian academics and professionals residing in the USA. The motivation is to pay back the homeland and help elevate the level of education in Algeria. INAS's mission is to network Algerian competencies worldwide with counterparts in Algeria. Among its activities, INAS has organized a significant conference that took place outside of Washington, D.C., USA in 2019. The conferees identified several need areas in Algeria and agreed to work on 10 different projects covering areas ranging from education, healthcare, to agriculture and ecotourism, to name a few. The work is ongoing and progressing. INAS is adopting the most contemporary and proven scientific methods to address these issues. INAS's humble beginnings included a few members. Today, it accounts for hundreds of able Algerians from the world over. Their goal is to participate in the rebuilding process of our new Algeria. These able and proud Algerians combine diversity and expertise with benevolence to set a path for a bright future in Algeria. INAS uses a top technology platform to allow members to collaborate and exchange knowledge. As an organization, INAS has different departments that ensure professional support to all its members, projects, and events. We welcome all Algerian competencies worldwide to join us in our noble mission. Algeria is bigger than all of us. Let's stand up and be counted today.